On behalf of Melbourne Museum and the Maths Association. Melbourne Museum has been incredibly supportive of this series over the last few years, and we're just delighted with that level of support, and it's wonderful to see the audience for these public lectures grow every year. So we thank the museum for their support. And don't forget, if you're a student or a teacher, entry to the museum is free, so don't hesitate to wander around the museum before you wander up the road to lie down the street for lunch. I just would appreciate a quick favour, if you don't mind. I just want to prove that people turn up to these things. So I'm going to take a photograph of you all, if you don't mind. So I hope everybody's ready. And you can all say, can anybody think of a mathematics word that says cheese? Anyway, cheese! Thank you, you look wonderful. These lectures are only possible because of the generosity of Marty Ross and Burkhard Polster, two academics working at Melbourne University in the case of Marty, and Monash in the case of Burkhard. And they decided quite some time ago that if the mathematical world that they love and understand is to have any relevance and meaning, it ought to be something that other people start to understand as well. So they've set out to become mathematics communicators and to try and get difficult ideas across to we mere mortals who find it a little bit difficult sometimes to bend the brain, and they help us do that. And that's the purpose of these lectures. Now, the Mathematical Association of Victoria has as its mission the valuing of mathematics in society. Now, that means that we want to see mathematicians prosper and their work appreciated and valued. But our most important work is in schools. And when you think about that word valuing mathematics, the word valuing, it doesn't mean people understanding that maths is important or people even just getting their maths right. It means kids in schools actually valuing mathematics, and that means, I think, understanding the importance of mathematics in our world. And I don't mean just today. A lot of what we do in mathematics classes is, making it real. So we take kids to a production line and say, understand the maths of that. But actually, there's a richer meaning to that idea of valuing, and that's perhaps understanding the cultural importance of mathematics, understanding how mathematical ideas came about at the time they were needed. People needed to learn how to build things, so they had to invent principles. They had to come across these ideas. They didn't just come out of the ether. They were actually constructed by people observing the world they understood within their culture. And Marty and Burkhard have, over the years, helped a lot of us understand a lot of those things. This year, we're looking at mirrors. We're looking at the Poincaré conjecture and its recent solution. We're looking at the joy of gambling. And I thought that's a funny thing for the maths community to be talking about, what the wonders of gambling. But in fact, the joy of gambling, from Marty's perspective, is there's no way known you can win. so he might help share some of that with you this year as well. And we're also going, for those of you who have friends and colleagues elsewhere in Victoria, we're going to be in Castlemaine and Bendigo on the weekend of the 17th and 18th of August, and sharing with schools and other people in Bendigo, Ballarat and Castlemaine some of these wonderful public lectures. So without further ado, please welcome the Mathemagician, who's going to help us look through the looking glass. Burkhard Polster.
Yeah, so maybe I start with actually, if you ask for a word that you should use instead of cheese, I would have used pizza. Pizza is very mathematical. If you just think about it, pizza starts with pi, right? Then ZZ, which is Z squared, and an A. So if you do pizza like this to the radius Z and the height A, then you've got the volume of pizza, by the word pizza. Okay, but you've not come here for pizza, you've come here for mirrors. So let me take you for a tour. I mean, this tour has been quite popular ever since Alice went for her tour through the mirror, right? Alice in Wonderland, a couple of 100 years, no, 100 years ago. So let me take you through the mirror here. We're here in Wonderland. Okay, warm exercise for you. This is supposed to be a mathematical talk section. That one didn't like me. It's actually not going to be terribly mathematical, so I have to sneak in some mathematics at some point. So let's do it here. We've got a sum here, and I claim this is really correct. 340 plus 437 plus 74,813, and it's all going to add up to 43,373,414. Correct? No? Well, I tell you, this is correct. I'm going to demonstrate this. Okay, I've got and sadly my pretty assistant is at home, I'm a 4-year-old, but anyway, you have to go like this one. Okay, so what can I do to this to make it right? Well, I stand behind the mirror, and I go like this. Can you all read this? Yes? Okay. Right. Okay, everybody impressed? All right, another warm-up exercise for you. It's a party trick, so you can all try this on all the people who are not here today, right? What you need for this is, well, typical party setting, so you need a glass of wine. You empty it first, okay? So it's very important for this trick. You empty the glass of wine first before you try this. Then you write 2 words on a piece of paper, carbon and dioxide, all right? Now in a moment you see why it is important to empty the glass first. So here's the trick. So you take the wine glass, and if it hadn't emptied it. Okay, now you look at the 2 words through the stem of the wine glass, and you see that carbon turns upside down, and dioxide doesn't. Ooh. And go back, still the same. So anybody's got any explanation for this? It obviously has something to do with the different colors we used, right? Not? Oh, okay. So any ideas why does one turn upside down?
Because dioxide is symmetrical through the line.
That's exactly it. So the letters here are really very special, right? If you flip these letters over, they actually stay the same. Right? Whereas in carbon, all those letters, except for the O, they don't do this. You can, if you don't have a mirror at home, if you don't have a wine glass, but you have a mirror, you can also do this with a mirror. So here's carbon dioxide, all right? What I do now, first is you have to turn it 180 degrees, okay? 180 degrees, and then you turn around and hold it to the mirror. Can you all see that? So exactly the same kind of effect. So you turn it upside down. So if anybody can't see that, I mean, you might be a little challenged here to see these things. Can you see these things? Or shall I go slower? Better? All right, I'll do it like this. But usually I'll have my pretty assistants here, right? Okay, now for serious stuff. I just wonder, I mean, how many people actually came here today because they wanted an answer to this question here? Anybody? So not such a burning question after all. But I mean, this is a question that has been asked for thousands of years, right? Ever since anybody looked in the puddle and observed that, something weird's happening here, people have been asking this question, I would assume. All right. Why do mirrors exchange left and right, but not up and down? I mean, somebody may have asked you this question. If you look it up on the web, there's about 1,000 answers to this. All more or less confusing. Some right, most of them are wrong. So I thought I might just give it a good shot and give you my answer and see whether I can convince you to the right way of looking at this. So first of all, we have to kind of make clear what we're actually asking here, right? So we've got the Melbourne Museum, and I'll just take a picture of this. So there's a picture of the Melbourne Museum here, and what I do is I hold it up to a mirror. And what I see there in the mirror is what you see there on the left side, right? So there's the mirror image, there's the original here, and the question is really about Well, we've got the top of the tree here, we've got the top of the tree there, we've got a bottom there, we've got a bottom there. So bottom stays bottom, top stays top. But when you look at the left side of the picture, that goes over to the right side. And if you look at the right side, that will end up on the left side of the picture. And why is that maybe a bit puzzling? Well, think about it, right? You've got a flat mirror. The top and bottom sides are in no way distinguished from left and right. Still, the mirror has this tendency to, flip two of those things around, whereas it leaves the other two the same, right? Shouldn't it, if it switches anything, switch everything, like switch top and bottom and left and right? And, well, if there is this, for some reason, a good reason why there should only be one switched, why is up and down left fixed and not left and right? So this question kind of breaks down into maybe two individual questions. All right. Now I made up this particular question a couple of months ago, and I thought, well, that might be a good one. But maybe the reason why you're all not interested in this question is because you all watched The New Inventors 3 weeks ago. And in The New Inventors, it's an ABC show, two of the science gurus there actually gave an answer, and I just want to show you what they had to say.
Why do mirrors reverses from left to right, but not from head to toe? Alec from Pingelly in Western Australia.
Modern mirrors have a layer of aluminium or silver on the back of the glass. It was a process invented back in 1835 by Justus von Liebig. But the earliest mirrors were made of highly polished metals, bronze, silver, or even gold.
Mirrors seem to reverse us, turning left to right, but they don't really. Don't confuse your left and right with the mirror's left and right. When light rays strike a mirror at an angle, they come off at the same angle. So if you're standing right in front of a mirror, what lies on the right reflects back on the right, what lies on the left reflects back on the left.
When this little person faces the mirror, the green glove always points to the right in reality and the reflection. Red gloves point left. But thinking of left and right with mirrors can be confusing. So let's think of north, south, east and west. Now we can say green gloves, always east, red gloves, west.
But you can reverse your image in a mirror, or rather, two mirrors at right angles. Now, light from the right bounces to the left, from the left it bounces to the right, and so in that image here, I see myself truly reversed. I see myself as others see me. So Alec, if you want to get an image in the mirror that's upside down and left to right, you'll have to stand on your head.
But here's a mirror puzzle for you. Why is your image the right way around at the back of a spoon, but upside down at the front?
Right. So, everybody happy with this? Well, everybody looks pretty happy, so in this case, I'd say this is the end and thanks for coming. Well, personally, I'm not terribly happy with this question, this answer. And I'll tell you in a second why I'm not happy with this. Let's just go back to, the setup that I had at the beginning. So here we've got the scenario that we want to consider. Right? I mean, I'm sure the person from Western Australia is asking about something like this, right? And it's a legitimate question, a question that people have been asking for thousands of years. Now, what the science guys are really doing is to say, well, it's a silly question, right? So let's talk about something else. Let's talk about mirrors. Right? But so they don't really take the question seriously as it's posed. So what they're doing is, well, they look over some person's back, say left stays left, right stays right, up stays up, down stays down. It's a perfectly valid observation. In fact, everything except one thing they say in the clip is correct. It just doesn't answer the question. So that's a bit odd. Anyway, so let me try to answer the question now. Again, right? Keep in mind what we're really asking here, right? We've got this kind of setup. We're looking at the original, the mirror image, and we're observing up stays up, down stays down, left and right get exchanged. Why is this so? All right. Now again, the pre-assistance is missing. It's terrible. So the first thing I want you to do is, have a look at this. What does it say? Mirror. All right. So when I actually hold this up to the mirror, what do you see? Do you see mirror in? Oh, I have to go like this. Okay. So everybody's seen the mirror image now? Can you actually see the mirror image of this mirror somewhere else than the mirror? Well, if you hold this up to the light, if you hold this up to the light, you can actually also see the mirror image. Right? So what that means is that, well, the original and the mirror image are really two sides of the same object, flat object, right? So you've got this flat object here, and you turn it like this, and you get both the original and the mirror image. And I think this is a good way of looking at original and mirror image, because you don't have to kind of physically kind of go from one object to the other. You're only dealing with one object, basically, right? The mirror image and original are the same thing. Okay. I've got a bit clearer here, just turning it around like this. So, original and mirror image. Now, think about this. I give you two photos and I stumble and they fall on the floor. Right? What do you do when I ask you to put them right next to each other? You pick up one of the pictures, right? And you look where's top here. So you make top face up. And then you pick up the other one and kind of quickly spot, oh, there's top, and then you kind of put them right next to the other. And that's a choice that you make. Right? It's a choice that you make. It's a choice how you put two images right next to each other. Okay. So now work those two things together. We've got the original and the mirror image, which is just this one object here. Right. It's two images. We put them right next to each other. What do we do to put them right next to each other? Right. We first identify where's the top here. The top is here, and on the other side exactly the same spot, right? So exactly here. And how do we move from one image to the other to put them next to each other? We turn them around this axis. And what do we do here? We hold on to the top, we hold on to the bottom. So top and bottom don't change. Left and right get swapped over. So it's quite natural. It's quite natural that this should happen. But it's just kind of another way of saying, well, left and right switch over. But we're kind of getting there. We're kind of getting there towards the explanation. Now, if this object here is original and mirror image, no matter how you go about comparing the two, one thing you have to absolutely do is you have to flip around some axes. Right? I can flip around this axis here, or I could flip around. I could flip around this axis to go from one image to the other one. I could flip around that axis to go from one image to the other one. I could flip around this axis to go from one to the other one. There's no choice. To be able to see these two things next to each other, you have to flip across something. And as soon as you flip, you hold two points fixed, which means one axis is fixed, and the other axis gets swapped over. So if you switch across this axis, then left and right will be switched. If you cross this axis, up and down will be switched. That's not a choice, right? So kind of the first paradoxical thing about looking at the mirror and asking, well, if something gets switched around, there should really be both things switched around. You can see in this way of looking at original and mirror image, that's not the case. It's kind of just a misconception about us, putting something into the picture that's not there. If you look at original and mirror image, you have to switch the axis. So something has to be fixed and something perpendicular to it has to be switched over. But why is it up and down that are left fixed and not something else? Well, that's really our choice. That's our choice. It's our choice of making up where's the top in this picture. We say that the top is here. If we had said that the top is here, we would have gone like this. Right? And you can also see this in another setting. Let's just imagine we're kind of in the middle of space, and we're looking at a flat object like this that doesn't have a predetermined up and down. So I've got my little daughter's hippo here, a favorite pink hippo. We're going to now look at hippo in space, okay? So hippo in space, you want to go one back? Back. Okay, hippo in space. Hippo in space approaches a mirror. Hippo in space approaches a mirror. And this object is hovering in front of the mirror, right? Now, hippo in space is kind of carrying an up and down around with it, right? So hippo in space approaches like this. So what it immediately kind of says here is, well, blue is up. Why is blue up? Because I'm up this way. Okay, and now I'm going to compare original and mirror image by flipping around like this. which means that this axis is fixed and these two get flipped around. But if Hippo for some reason approaches this object in a different direction, like so, then what you get is Hippo will say, the red dot is up, the orange one is down, and then it will put the pictures next to each other so that blue and green get swapped over. So there's really two things that contribute to this effect of switching left and right and keeping up and down fixed. The first one is, any way you want to compare original and mirror image, you have to flip across the axis. Okay? And the second thing is, we make an arbitrary choice in what is up. So that's my personal explanation for this question. And I don't know. Do you like this better than the other one? If you like it better, good. But still, you may forget my explanation. So remember the other one. It's really good if you want to shut somebody up quickly. Right? So basically, you say, silly question. Let's talk about something else. So it's a good one to remember. This is a bit more complex. Just a little bit more involved. All right. So some people like this better. Hands, who like it better? Say you like it better, please. All right. Now, if you have a picture of something like the Melbourne Museum, you can hold it up to the mirror like parallel, but you can also hold it in various different ways. And what I've done here is I've just put the original here and put various mirrors at right angles. So there's a mirror going this way, mirror going that way, mirror going that way, mirror going this way. Right? And really, if you look at the original and the mirror image here, what you see is, well, the mirror image doesn't really change, right? This is the mirror image that we looked at before. So this mirror image here is really the same thing, just kind of, you turn this one here slightly like that. And then that mirror image is really the same as this one, it's just kind of turned upside down. So there's really only one mirror image when you think about it, just kind of turned around in space a bit. So you can look at this mirror image and mirror image original combination in various ways. Here's just the usual juxtaposition that you would do if I give you these two things separately. You just put one right next to the other, and you find this, top and bottom fixed, left and right swapped. But you also get this view quite often here, when you have like a puddle in front of the Melbourne Museum, right? And in the puddle you see a mirror reflection of something. And in fact, here what you see is the top and bottom get switched, and the left and right get left alone, right? So whatever is left here stays left, whatever is left here stays left, whatever is right here stays right. And you can again explain this. It's basically us importing our notion of what is up into the, into the setup. And then to move from one object to the other one, what we have to do is we have to flip like this. Right? So we have to flip around one axis. So these are two views of the same object, put them next to each other, and you move from one to the other by swapping across an axis, and you import your notion of what is up into it, and that leads to the effect or the question, why does a mirror exchange up and down and not left and right? Usually it is not asked, I don't know why. One version is more popular than the other one, but this one is just as legitimate. Maybe a couple of thousand years ago when people were kind of relying on looking in puddles to see mirror images, maybe they asked this question more often. But now, since we have all our mirrors mounted on the wall, the other question is taken over, right? Maybe. I mean, there's very few puddles on the wall, right? Okay. So I found this one clip on Australian TV. I found another one. My little daughter's favorite TV program is The Funniest Videos. And it's always on Sunday, so we all watch it religiously. And we found a good mirror clip in there, which shows you that mirrors can be quite confusing.
I say, the standard of new dog at the palace is really dropping these days. Take a look at this latest number. He's as ugly as sin, and gets right in your personal space. And the spineless blighter scoffs as soon as you stand up to him.
So that was a good clip. There was another one which was even better, with a spider. Has anybody seen the one with the spider?
No.
But I couldn't just feel like I should have, well, no mirrors in it, so I couldn't do it. Okay. Now, now here's the warm-up exercise for the second part of the lecture. Wait. You have to see this. Well, I mean, Marty knows that I like to juggle, so he gave me 3 of those. You know. The idea is, you catch this, and as you catch it, the eye pops out. I'm still working on this, so I can't demonstrate it today. But there's another lecture about juggling in a couple of weeks' time, so maybe by that time I've got this down. Okay, so today I'm just using this to cover the top die, and they're about to shut the doors here. The thing is, you cannot leave this room unless you tell me what's the number that's hidden below the skull, what's the number that's hidden below the red die. So I want the number that's here on top of the yellow one, and I want which one is here on top of the blue one. So it's all locked now. They're about to weld it shut, right? I'm waiting.
The red one's 5 and 2.
Say it again.
The red one is 5 and 2.
So somebody says 5 and 2?
Yeah, top and bottom.
Top and bottom, but which one is top? And how do you know that it's 5 and 2? How do you know it?
Opposite sides of the dice add up to 7.
That's right. So there's the first rule here. Opposite sides of the dice add up to 7. Always, right? So if you see a 3 here, then you know that on the opposite side there's a 4. And if you see that there's a 1 here, then you know that on the opposite side there's a 6. So 3, 4, 1, 6 are gone. So the rest has to be 5 and 2. Very good. However, you still can't get out because you haven't told me yet which one is on top. Now, you may make a guess, right? 5. All right. Yeah, but then what about this one here? Well, let's just check. Let's just check. There's a second rule that helps you. There's a second rule. There's really, with this kind of arrangement here, you find always a corner. You find a corner of a die like this, where you can see 1, 2, and 3. 1, 2, and 3. And you can see 1, 2, and 3, if you follow it around, it kind of goes in the clockwise direction here. But of course, it could also go in the counterclockwise direction. But it now turns out that it always goes in this direction. And that gives you a hint what to do. Because now what you can do is, you see 1 and 3 here, 1 and 3. Right? So what you do is, you move that die around. Right? And can you see this in your mind? You kind of move it like this. So the 1 goes over here, the 3 goes over there. So what's on top? 5. Okay. Some people may be able to get out of here. So 5's on top. Right? And then we do the next one. And we see, well, opposite 5, there should be a 2, right? So you can kind of imagine the 2 being there in the back, right? So what you do is you take this dice up there and you turn it around. It moves the 2 into the back. So what's on top? Who thinks it's 1? Who thinks it's 6? All right, let's have a look.
Yes.
Not too bad, so you can go. And you do the same thing with the last one, and that's it. So really nice trick. You can actually play this as a kind of a magic trick. So instead of having just 3, you do like 10, and you just stack them up for you, cover the top with a coin, and you turn it around, and you just go, and everybody's really, really impressed, right? Yeah. Okay. All right. Now, what I really want to do is I want to really take you on a journey through the looking glass as physical beings, and let's have some talking about what mirrors do to three-dimensional objects. Well, mirrors don't do anything to three-dimensional objects, but let's just pretend they do. Right? So the first thing is, this is a three-dimensional object, and this is one, 2, and they're actually mirror images of each other. So basically what I'm saying in rule 2 is that only one of the 2 possible incarnations of a die actually appears, right? So if you kind of come across the dice in nature, right, and just pick it up and you figure out, well, which one is it? it's always going to be the counterclockwise one. And there's, of course, the odd exception, right? Because people want to have exceptions. But in general, you will always end up with the choice here on the left. Okay, and this is actually something that we'll find happens quite often in nature. So let's say we are. Oh, this is, by the way, Lara, who couldn't get Michael today. This is the pretty assistant who would this is a hippo, and this is the hippo's toothbrush, okay? And both Lara and the hippo are right-handers, as you can see, right-handed, and the hippo holds the toothbrush in the right paw, right? And when you look at this other person here in the mirror, you see, well, I mean, they're both left-handers, right? Both left-handers. And I really want you to imagine that this person there is there, right? So how do you turn this person here, the original, into the mirror image? We can kind of think of the mirror as a supreme commander, and individual particles in Lara's body as the troops. And the supreme commander says, on my command, you all rush towards me, straight on, right? Straight on. And you cover a certain distance, and you don't stop until you've covered the same distance on the other side of the mirror, and there you stop, right? So everybody kind of starts rushing towards the mirror, passes through the mirror, and stops at exactly the same distance on the other side of the mirror. And when everybody's done that, you actually physically see this person take shape on the other side. So that's how mirrors, if they did anything, would create a mirror image on the other side. And here we kind of go back to the science guy's explanation, what they had before. What happens here is, well, things on the left kind of stay on the left, things on the right stay on the right, things at the top stay at the top, things at the bottom stay at the bottom. But what they didn't tell you is that things in the front, like something like this here, a particle like this, actually end up in the back. Right? So there's actually something happening. I mean, if you take this mirror, do something to three-dimensional object view, there's actually something that does get exchanged. Kind of the inside gets exchanged with the outside. What you do is you kind of take the original and kind of squeeze it through the mirror like this, right? So there's two extensions that are kind of parallel to the mirror. It's like this one and that one. And there's one that's perpendicular to the mirror. And the one that's perpendicular to the mirror, that's, when you take this view, really gets switched around. And there's a kind of a funny extension to what the science guy said here. If you turn the hippo around and make it go sideways, right, then the hippo's left and right is actually the direction that gets switched around. So, here, front and back don't get switched around according to the science guys. Top and bottom don't get switched around, but actually the left and right do get switched around, right? So, if you take this alternative view, you can actually make up things so that it gets switched around. But it's a different thing from what I talked about before. And here, if you put the hippo on the mirror, actually the top and bottom kind of get exchanged. Okay, now we really want to get to the other side. I don't really recommend that you try this, right? Stand in front of the mirror and then somebody squeezes you through. It's kind of a painful process, which, it has maybe been done, but usually you kind of end up in the flat position, right? So if, say, something falls on me and makes me flat, right? It's exactly what happens. Everything goes at right angles towards the floor, but then it's kind of, blood flows out to the side. That's it, right? So, I don't really recommend this. But let's just imagine we could maybe somehow just step through the mirror like Alice does in her adventure, right? So would that be a good idea? Would it be a good place to go? There might be good real estate over there. It's really cheap, right? We're running out of things here in Melbourne, so maybe you just go to the other side. Mirror, Looking Glass Land, maybe houses are really cheap there. Well, nobody can read the prices anyway, so. Okay, I have to tell you a little bit about mirrors. More about mirrors. Mirrors, when you take this view that the mirror really creates something on the other side, split the objects of this world into two different classes. Those are their own mirror image, and those that are not. And let's just have a look at what I mean by this. If you look at this letter A, that's a flat object, right? And you think of all the objects that I'm going to talk about from now on as made from material that can pass through each other. Right? So, if you take this A here and just kind of slide it over to the other side, you can make the A and the mirror image come on top of each other so that they become indistinguishable from either that or that. And when they do this, I say the object is its own mirror image. So A is its own mirror image. So what about this Kermit Frog shadow? Because there's Kermit Frog, the shadow, right? I can move it around any way I want here in the plane, right? But I'll never be able to make it coincide with this shadow. But there's a trick that I can do. What I can do is I can take the shadow and I can kind of flip it out into the 3D world and just kind of make it go over like this. And then it actually coincides with itself. Right? So, I mean, the 3D shadow of the Kermit shadow is its own mirror image in this way. And in fact, anything that's flat is its own mirror image. So what about real three-dimensional objects like a left hand, right? A left hand. You look at the left hand in the mirror, the left hand turns into a right hand. Turns into a right hand. Can you take these two objects, move it through space, and make them coincide? No, you can't. So you can put them like this, but they're facing the opposite direction. So you really kind of want it like this, but no, it doesn't work, right? So these two objects here, left and right hand and mirror image of right hand, they are not their own mirror image. So this is not its own mirror image. It's not its own mirror image. So these really split up in a pair. What about the chair? Is the chair its own mirror image? Won't? Yes? Are you sure? The doors are not open yet, right? So you better make up your mind. Okay, so the chair is its own mirror image, and why is that? Because we can kind of cut through the middle, and you can see that. You just turn it around and move it in like this. It will be its own mirror image. Same with this cube. Okay, so how would you actually know in a flash whether an object is its own mirror image or not? Well, if you kind of go back to this plane figure here, the A, it's its own mirror image. And it's got this nice axis in the middle. It kind of cuts it into two parts that are original mirror image. So if it's got an axis like this, here the same kind of thing with the chair. We can cut with a plane through the middle, and the plane cuts the chair into basically two parts that are related by the mirror. Right? So is this always the case? If you see some three-dimensional object, and it's its own mirror image, do you necessarily find a plane that kind of cuts it in half like this? What do you think? Yes or no? Yeah? Okay, no. Got you there? Okay. So here's how you make an object that doesn't have this property, but is its own mirror image. What you do is just take two copies of this. You fold up like that. These two are mirror images of each other, right? So just imagine that there's a mirror here, right? There's a mirror here. Then you can see the mirror images. And what I do to bring them into coincidence like this. And if you look at an object like this that doesn't have a mirror plane built into it, right? Just a mirror plane. That's kind of not what you would expect. So there's a bit more to it than meets the eye. All right. So now we're ready for the real trip through the looking glass. Is it a good idea to step through the looking glass? Or, would something terrible happen if you do so? What do you think? Is it a good idea? What do you think? You want to go?
No, because otherwise I'll crash and I would get injured or something.
Yeah, crash and burn. We'll see. Okay, let's have a look at how left and right, or original and mirror image, or left-handed and right-handed, comes up in nature. Let's have a look at these snails. So a snail shell like this is not its own mirror image. But you can find snails like that, and you can find snails like this. Right? So basically, roughly mirror images of each other. If you pick up a random snail, what do you expect? Do you expect to have one of those in your hand? Or do you expect to have one of those in your hand? What do you think? They're both slimy. All right, they're both slimy, but you end up with one of them, right? Do you expect to have roughly 50-50 chance of having this one and having that one? Or do you think it's something else? Well, I'll tell you, okay? Oh, that one? Okay. He's right. Out. This guy knows too much. This one here. The ratio of these kind of snails to those kind of snails is about 20,000 to 1. Right? How do we know this? Because in France they like snails, they have snail farms. Right? And basically they have like lots of snails there, and they have a special kind of corkscrew to kind of yank them out of their shells. Right? And if I accidentally hit one that's not in this direction, then you know immediately, and you get really, really good statistics about the ratio of these kind of snail shells to those kind of snail shells. So there's a kind of imbalance. Just like with the dice that we had before, there's an imbalance. If you pick up something random in nature, which has a left-handed and a right-handed version, you always find that one of the versions is preferred. Here's another really extreme example. The conch shell. I mean, what you usually do with this is you kind of cut off one part and then you kind of blow on it. That's exactly what the Lord Vishnu does on this side here. The ratio between the left-handed and the right-handed version of this is 1 to 100,000. So one is really rare. If you find one of those, you're basically, set for life, You just have to steal that one. That's a rare one. Right? So whenever you see the Lord Vishnu as one of those things, it's always the rare one, which should be really. But you still get kind of the slight imbalance. You still find this occasional rare exception. But that stops when you kind of go down to the molecular level. And there's a really nice phrase in Alice in Wonderland where Alice talks to her kitty and asks, well, I wonder if they gave you milk in Looking Glass Land, what would it taste like? Would it be good for you? Would you die? What would happen, right? And it's a legitimate question. If you look at molecules, and especially those in living beings, like amino acids and carbohydrates, most of them, the vast majority, come in a left-handed and a right-handed version. And if they come in a left-handed and right-handed version, it's always one version that's preferred. So you only get this, like, if you find alanine, that's one of the molecules that I was just talking about, in your body, it's always going to be this one here. Right? It's always going to be this one. It's never going to be that one. And our whole life is built on this bias towards one-sidedness of the molecules that we're dealing with in living beings. Like metabolism is built on this. If you eat something, it has to have the right-handedness for our body to actually be able to absorb it, to do something with it. If you feed it something from Looking Glass Land, our body doesn't know what to do with it. That has strange effects. So, I mean, I'm just telling you now, if you step through that looking glass, okay, on the other side, I mean, the first thing you have to think, well, I have to start breathing now, right? What will happen? Well, let's have a look at the air molecule. And great, I mean, air molecule is actually its own mirror image, so nothing will happen. You can breathe. What about drink some water? H2O, yeah. It's its own mirror image, so nothing will happen, right? But if you drink milk, ooh, danger, right? If you do anything else but stand still and, be scared, you might actually end up dead, You bite into this really nice looking apple, you may end up dead. So, think about it. And every once in a while, something from mirror world actually makes it into our world and creates havoc like this. And a really famous example for this is thalidomide, which was a medication that was introduced around 1956 or 8. And it comes in two versions, left-handed and right-handed. And you're probably familiar with the story. It wasn't tested properly, and we ended up with 12,000 children all over the world being born with deformities. And the reason for that is that the body could really only do something reasonable with one of these molecules, but not with the mirror image. The mirror image was creating havoc. And the mirror image and the original were kind of created in equal amounts in the chemical process that people were using at the time. So, created a huge disaster, and it's really, mirror world looked like visiting our world and doing terrible things. So be careful when you step into mirror world. It might not be such a pleasant place. Okay. What else do I want to say about this one? Now, we've been giving, like Martin and me, we've been giving talks. We've been giving talks here in the museum now for 6 years, and I've come across lots of things in those talks where I can actually talk about, original and mirror image. And there was one last year about the mathematics of magic, where I actually talked about, this business about getting into mirror looking glass land. So it is actually possible, and we don't really know whether it's mathematically speaking, it is actually possible that we may be able to turn ourselves into our mirror images. So it may be possible that you go for a trip somewhere, right? Some faraway place. You go to a trip somewhere, faraway place like what's one of those mythical places? Say again? Oh, that's a good one, right? La Pucha, so we go to La Pucha, right? And then we come back, and then we come back reversed, right? So without knowing, by going through this journey, we may come back reversed, and then we bite into the apple and die. It might happen to you. It's not completely out of the question, and I'll just tell you why this is so. Let's just think about these flat things. So this is like a flat person. And the flat person, the natural habitat of this flat person is really kind of a plane here, right? So it's like a plane. But if the flat person can somehow figure out how to move out into the three-dimensional world here, what he can actually do is kind of turn himself upside down. So if he, for some strange reason, in the course of his journey, ends up in a place like this, he can actually go back to the beginning, mirror reverse, and be out of luck. And the same kind of thing can happen to us if our three-dimensional space has an extension to a four-dimensional space, then we might also somehow end up there in four-dimensional space and turn ourselves around. But it gets even more wicked, and I'll just show you, even if there is no surrounding space, you can actually be unlucky if the universe that you live in is of the wrong shape. So this is a strange kind of flat universe that this person is living in. If the person goes for a circular journey around this, it will actually come back mirror reverse. I'll just show you how this works. Now it's mirror reversed. I'll just turn around a bit. So now he eats the apple and dies, right? The same kind of thing is theoretically possible in our universe. If our universe, for some strange reason, links up in a strange way somewhere out there, then we may go for a trip in a spacecraft, come back to Earth really happy because our provisions are all out, bite into the next apple and die because we turned into mirror images. It's possible. So it's just one of these weird things that can happen. So various ways of getting through the mirror, right? Like straight through, not to be recommended because you end up as a puddle of blood, right? The next one is kind of like Alice, you just kind of step through. And then the third one, which is an actual possibility, it's not been excluded by physics or anything else, is that because of the shape of our universe, you can get, you can end up in mirror land, looking glass land. Okay. So just a bit of fun towards the end. This was all kind of heavy, This is by a friend of mine, a New York artist who makes up words that kind of incorporate mirror reflections. This is life and art written as mirror reversals. Let's just do a bit of art here. This is MC Escher here. One of MC Escher's pictures called Magic Mirror. Some writing has been edited. This is by an artist called Scott Kim. It's the word mirror written such as it's its own mirror image. So very cunning. Right? And here we've put that word into Escher's picture so that it's kind of written on the floor, right? And it doesn't extend over here as itself. You really see it extending as a mirror image. So it's kind of something very cunning here. And the magic on top kind of just extends this way of writing mirror. This is something for teachers. Who's a teacher here? So you may like this, Teach is the reflection of learn. So this is something nice. It's by the same person, Scott Kim, so the same person who made up the mirror. That's by me. So that's geometry, right? As a mirror reflection way of writing it. And then this is really a mirror. This is not like a transparent piece of glass. This is a mirror. So what you see here is not the right side of my face, but it's the left side of my face in the mirror, which kind of fills in reality like this. And this is also just I wonder why I have the t-shirt inside out, because And too late, I figured out, well, I've got this writing here, and it would kind of mess up everything, so I had to wear it inside out. There's a French artist who does a lot of nice work with these kind of games. So it's like transit, just half of written in neon, and then you see the reflection kind of completing the word here. And over there you've got Second Regard, so it's all a bit French, of course. There's one in one of the Hyatt hotels in Paris. You see this, Française? And in the mirror it actually asks, is this English? Right? Is this English? No, this is French, right? That's a very nice one by a friend in California. He's a mold maker by profession. And you may have noticed this, when you spell life backwards, you get evil. This guy knows too much. Okay, life backwards is evil. So what he's done here is he's got these really nice toys, a laser cutter. So he's taken a piece of leather and he's carved life in such a way that when you read the strip from one side, you read life, 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 life. And when you read it from the other side, you read evil, 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 evil. And then you spun it into this nice spiral, and then kind of when things turn around, when you go from front to back, you see the life turn into evil, and then life, evil. And when you look at the mirror image of this, it's just a straight mirror image, things kind of turn inside out. It's a kind of very nice magical effect. See how we're going? Still well. There's something else about spirals that I've noticed. If you go to, I'm from Germany originally, so we've got more churches than houses. And so you go to any of those things, right? They're all built like Baroque. They all have these things in it. Altars that are framed by spirals. So if you look at a spiral like this, that's actually the mirror image of a spiral like that. Right? And when you just look at the slants of things here, kind of this column here slants in like this, the mirror image slants in like that, right? If you were to swap those two around, then of course they would both slant like that. But in all the altars that I know, except for one, everything is slanting like that. And in fact, when you have a close look at these setups, what you see is there's a nice kind of optical illusion happening. And the optical illusion is that if you've got, two parallel strips with slanting things going across, then what they seem to do is kind of converge at the top. And although these pillars or columns are completely straight, when you look at them from far away, you really see as if they're kind of converging towards the top, towards heaven, right? There's one exception here, where they're actually going the other way around. But when you look at what they're actually depicting, it's kind of a descent into hell, right? So there's things going down, it's like a funnel going the other way. So the optical illusion is really directed the other way. So the artists around that time really made very good use of these kind of effects. That's kind of art. There's lots more I could say. So maybe the last thing I want to do is, really run out of time, there's 3 options here. You can choose. First one, what does left-handed and right-handed have to do with the way you tie your shoes? That could save your life. Okay. The second one here is answer the question, why does this happen here? The third question here, how do you impress your current love interest? Your choice. Make your choice, you made your choice. Who wants shoelaces? Who wants that one? Who wants love interesting? Okay, I'll just start with one. Okay, I'll start with one and see how far we go, right? I just ask you whether you want another one. Okay, let's do this one first, maybe. Let's see, how do I do this? Nothing else. Right. So there is this, you see the hippo? I've got this really nice double mirror here. So from the local $2 shop, you get 2 mirrors. They cost $2 each. And it's a really, really nice toy, so you just tape them together with something like this. You put them at the right angle. That's one thing that the science guys talked about. If you do this, and you look in a mirror like this, then you actually see, right-handed hippo in the mirror. The way this works is the hippo here gets reflected on this side, and then you see a reflection of the reflection in here. So basically, reflection of reflection cancel each other out, and it works, right? But you can actually go further and explain the spoon trick with this right-angled mirror. Let's just take for granted that these right-angled mirror set things right. Okay? You can replace the right-angled mirror by a surface that's kind of swooshing around like that. So instead of having a straight angle here, it's kind of a little bit curved there. Right? You get exactly the same effect. So what that means is, if you hold up a hand to a mirror like this, then it will really look the right side around. And of course, if you turn this on its side, then you'll see that things get kind of turned upside down. So it really gets, if you look at it like this, you can really see yourself kind of upside down. So in a concave mirror like this, what you really see here is two of those mirrors joined into one. And you see the upside down thing happening, plus the left and right, but the left and right doesn't really stick out because we have kind of this mirror symmetry built in, so you don't really see this, but you see the upside down happening. And the outside curve, that just works like an ordinary mirror. So that's kind of the explanation for the spoon trick. So who wants to hear something else? All right, something you can play with this mirror here. So if you finish with looking at it at right angles, you can also so there you've got 3 aliens. Then you go at a right angle, so 90 degrees, you've got 4 aliens. And then at nice angles you get 1 more aliens. So you kind of start going in a circle. And if you like put a candle here, it looks really fantastic when you go really, really close. You've got these like hundreds of candles going in a circle. And actually, when you kind of bring them really close together, you get close to this effect of having infinitely many things reflecting back and forth like in an elevator. Okay. So something to try. Oh, maybe we just do this one here. The shoelaces. So this is something that may potentially save your life. How do we tie our shoelaces? We go like this. Roughly, right? Bunny ears, knot, pull. Okay, so here again, that's how I actually do it. Okay. Around like that. And now you try this at home, right? You try this at home. It's a bit of a mess here at the top. So you tie one knot, and then tie another really messy one on top. To really see what's happening here, you pull out the bunny ears, have a close look. You may end up with something winding like this. It's basically one half knot on top of another half knot. And actually knots come in left-handed and right-handed versions. These are 2 left-handed knots, one on top of the other. You can also change things around. So instead of going like that, you turn this into a right-handed knot. Bunny ears. Pull it out. And you get a slightly different one. Let's just look at them side by side. You either get this, or you get that. And about half of you will get this, half of you will get that. So you all think you're doing the same thing, but you're actually doing different things. And in fact, the people who do this one here, they're in luck. Those shoelaces don't come undone very often. Those will, right? So, but what you only need to change yourself into the proper version is the first knot you tie the other way around. That's very easily accomplished. The rest, the complicated bit, you leave unchanged, right? And the next time you're at the top of the stairs, you kind of start, falling like that, right? And you remember when actually I was this one, but I was too lazy to change things around. I told you, right? Anyway, I think we don't have time for the third trick, so I'll leave it at that. And yes?
When you're driving home,
yeah,
and you look in your rear vision mirror,
that's right.
all the cars behind you will be left-hand drive vehicles.
That's right. They will. Just like a right-hander goes in the right Anyway, if you've got any questions, I'm kind of losing my voice here. I'm kind of dead anyway. So, I may have some. Do you have some time or?
Time is up, I'm afraid.
Time is up. Well, if you've still got questions, just come up here in front and I'll try my best to answer it. Apart from that, thank you very much. And next week is Marty on...
Sure, gambling. Gambling.
Next week, you learn how to beat the casino, right?
Yes.
That's right? So Marty is an expert. He's been thrown out of the casino a couple of times, so he knows what he's talking about. Okay. Everybody here next week. Thanks.